Thank you very much for your very kind introduction. Good morning. This morning I will be presenting to you experimental research that we have conducted at the University of Ottawa in Canada on seismic retrofit of non-ductile buildings. These buildings primarily include non-ductile reinforced concrete frames and some masonry walls as well. So I would like to give a brief overview with the intent of giving you a glimpse of a number of projects. Seismic retrofit work at the University of Ottawa is done in two phases. One of them is to look at individual members, and this is when you have few substandard members in a given structure that you wish to retrofit and increase strength and ductility. If you have fewer columns, you may go and retrofit them. But if you have too many, then you may want to have system-level interference, in which case you're better off, of course, bracing the structure and have drift control. So in these two areas, we've conducted research. A large proportion of existing infrastructure is potentially vulnerable against seismic forces, and this results from either structures being old, designed and built prior to enactment of modern seismic codes, or they happen to be in countries where code enforcement creates challenges. First, I would like to look at column retrofit. And here you see examples that you're all familiar with. These are some of the bridge columns that suffered shear or compression crushing failure, or even some had splice slippage problems. And these are some of the examples taken from building columns, and they go through similar damage. And the first technique that I would like to present to you is transverse pre-stressing of columns. And this is unlike the way we usually pre-stress members, but if you provide transverse compression, so the column has pre-compression before the earthquake and during the earthquake, during moderate size earthquakes, they may survive without crack because it's already in compression. Diagonal tension cracks will not be able to open up. And the other advantage is that, as you know, when we confine concrete to improve strength and ductility of compression concrete under flexure, we induce passive confinement pressure by providing closely spaced hoops. But in this case, you provide not only passive confinement pressure, but you provide active confinement pressure by providing this lateral pre-stressing. So the way to apply is simple. If you have a circular column, you just have to wrap around, in this case, 7-wire strands and use a connecting anchor, which is the type that we use typically for pre-stressing circular tanks. And if you do have square and rectangular columns, we have to have razor discs, as shown here, to try to take advantage of hoop tension. And there's a student applying so-called retro belt, because they look like a belt, and before we pre-stress it on circular columns, and you see some of the application on square columns. Now I'd like to show you very quickly the results. These are shear critical columns. These are bridge columns having 500 millimeter square cross-section specimens in the lab. They're subjected to low levels of axial load, 15% of P0, because they are bridge columns. And on the left-hand side, you see brittle shear failure at about 1% drift. On the right-hand side, application of retro belts resulted improvement up to 4% drift. And you can see similar response in the square column just below. Now, these are the comparisons for flexure deficient, confinement deficient, flexure dominant columns. And similarly, if there's no retrofit, and these are the columns that have about a foot spacing between hoops, like 300 millimeters spacing. And of course, reinforced concrete has a little bit of inherent ductility. We were able to go up to 2% drift. under low axial loads, and that has improved up to 4% by the time we applied Retrobelt. This is our artist's view of how to apply it in practice. We did a cost analysis, and this is much cheaper than steel jacketing, and it's also cheaper than FRP jacketing, which is what I will discuss next. One other comment I'd like to make is, of course, they will not look as ugly as they appear on these slides. We've tested columns covered with shotcrete to protect against corrosion. One other way of doing it is to use column covers so they don't look like that in real application. Extending this concept to building columns created challenges because it's difficult to wrap 7-wire strand around a smaller cross-section building columns. So instead we tried using packaging strips, and these are high-strength steel strips that they use in packaging industry. They have 800 MPa strength, and they usually use a handheld device to crimp the strips, and we wrapped the columns similar to using 7-wire strands, except this is much easier, obviously, to bend in this case. Sometimes single layer, sometimes double layer. Here you see a student applying it on a column. And if you have square or rectangular columns, we prepared precast concrete filler materials to complete it to either a circle in the case of square columns or an ellipse in the case of rectangular columns to take advantage of hoop tension. This is always done in jacketing projects. And here you see the behavior as compared to 2% drift capacity in the non-retrofitted column. Now we were able to go up to 5, even 6% drift in this column. And this is the failure at 7% drift. And this is a square column which had shear deficiency. And one layer was not enough. We doubled the strips, and we again went as far as 6% drift before they started rupturing. Next, I'd like to go through FRP jacketing. This is a concept that has well been established in industry nowadays. You're all familiar with that. But we did do extensive research in the lab testing shear dominant and flexure dominant circular and square columns, as well as rectangular columns. And in fact, the outcome of this project has been incorporated in CSAS 802 Canadian standard for FRP jacketing. Once again, on the left-hand side, you see a shear damage, shear critical square column. On the right-hand side, there was a significant improvement using FRPs. And in this case, we use CFRP carbon fibers with roughly 9 millimeter thickness for each ply, for each layer. Now, what is of significant, and this was a major contribution in our standard, was how much of the FRP strength one should use in design. Because our FRP went up to 700 MPa strength, but can we utilize all of that? Because typically FRP jackets have lower modulus, and will it have the ability to expand and confine or improve shear capacity of the column? So on the right-hand side, you see typical coupon test results, stress-strain relationship, and FRP rupturing at about 1.2% strain. And on the left-hand side, you see measured strain, and you can see at 3 to 4% drift, we could not exceed more than 4,000 microstrain or 0.4% strain, whereas the capacity is 1.2%. So it was underutilized in this bridge column, which had small axial load. And similarly, when we used square and circular columns for flexure dominant, once again 15% axial load, we had observed similar response. And these are flexure critical circular columns, substantial improvement because here predominant mode was flexure. And once again, when you look at strain levels measured, they're all very low. We did not fully utilize, so one would obviously not take the entire full strength because it doesn't have the ability to confine it as the column dilates in laterally. However, when we used building columns under higher axial load, and here we went up to 47% of P naught, in one case, which was well above P balance, and on the right-hand side at about P balance 30%. And we tested circular and square columns. Square columns had either well-rounded corners or not rounded corners, because that was a parameter. Here you see we were able to actually rupture FRP. We were able to go up to 1.4% strain when axial load level was high. So it was then established that the level of axial load is a parameter in terms of taking design strength for retrofitting. The other parameter was the shape, and circular jackets develop more of the strain before the column started decaying, and square columns less so, and shape was also another parameter. Next, I'd like to move to lateral bracing of non-ductile reinforced concrete frames. And the first technique we developed is buckling restrained brace for concrete. As you know, BRBs are used, but mostly for steel structures, and we tried to develop a buckling restrained brace for concrete columns. And not only that, but the uniqueness of this system is the BRB being gapless. As you know, buckling restrained brace develop tension, and when they go through compression and when it yields in compression, it needs space inside to be able to shorten. I'm talking about the core element, and that's why there are gaps left. And under high deformations, they tend to buckle in those gaps. So we came up with idea of gapless BRB. So we created these fingers that would move in and out. They would engage, and throughout this tension compression cycles, the inner circular bar that we use would continue to be supported. So that gave us a fairly good response. On the right-hand side, you see hysteretic response of this frame, and as compared to 270 kilonewton capacity for the unbraced frame, there was a 3 times improvement in strength, and the non-ductile frame was able to go up to 2.5% drift. Obviously, if you are designing a BRB, one has to be aware of the fact that you're dealing with non-ductile frame, so drift control is important, and you don't want to allow too much drift to permit this non-ductile frame start developing failure. We did measure how much of the force was taken by the brace and how much was left to the frame, so that frame would maintain their gravity load carrying capacity, but those details I'm not presenting here. The next bracing system was transverse pre-stressing, and obviously this is tension-only braces, and we used again multiple 7-wire strands to introduce bracing. This was initially researched at University of Texas, Austin, after the Mexico City earthquake, but then the researchers did not continue. But I did see when I visited Mexico City after the more recent earthquake that they were implemented. So we tried to investigate effect of the level of pre-stressing and a number of strands as well. We realized that the yield strength of the brace was governing lateral load capacity, so there wasn't much improvement in lateral capacity. However, as the number of strands increased, and as the level of pre-stressing increased, obviously initial stiffness increased, and there was more drift control. So we thought this would be a great retrofit technique, but then we did dynamic analysis. Then we realized that the more we stiffen the structure, the more seismic forces obviously it attracted as expected. We were shortening the period. So then we tried to come up with another concept of progressively engaging cables. So the idea is we would use multiple cables, or even if we use single cable, it would not engage until it is needed. So that initially we would not stiffen the frame, and hence force demand will not increase. But if the earthquake were of higher magnitude, or if it continued, the duration is longer, then the braces would engage and start providing resistance. And if we did some tests as proof of concept, and it seems to work beautifully, but before we did that, we did some analytical research, and we looked at 3 cases. In each case, we had, like the case number 1, we had 2 cables. First cable would engage at 1% drift, second one at 1.5, and then we looked at 1.5, 2, and then 2 and 3 different levels. So before a technique like this can be used, obviously one has to establish drift capacity of the non-ductile frame. And here you see at different levels of engagement, the stiffness changes as expected. Before concrete crushes, that would be our limit. We were able to get 2.5 to 3% drift. And then we tested some frames, and we pre-stressed them. There were a lot of efforts at the ends to be able to pre-stress. And on the right-hand side, you see the results of single brace engaging at 1% drift, and hysteresis curves start showing increased stiffness beyond 1% drift. And here is the same hysteretic relationship compared with analytical predictions. And as you can see, analytically, we were able to predict. So one would use, obviously, analysis of the frame to establish its drift capacity, and accordingly, we would then use these braces. And next, we tested another frame. This time, we had 2 braces, or 2 cables. First cable would engage at 1.5% drift. So until then, the period would not shorten, and the seismic forces would not increase. But beyond that, the first cable would engage, and beyond 2% drift, second cable would engage. Once again, we monitor strains in the cables, and they did work as planned. And hence, we call them progressively engaging cables. Further research is being done on this concept. Now I will move from reinforced concrete to masonry, because masonry obviously is a brittle construction, and there are many masonry buildings, older buildings, that may benefit from retrofitting. So we used either FRP for diagonal tension control, or FRP and internal reinforcement if we needed flexural strengthening as well. Here's an example of using FRP for flexural and shear strength enhancement. We used homemade FRP anchors, so we anchored FRP to the foundation. That would be our longitudinal reinforcement, if you like, helping flexural capacity. And then there would be FRP anchors within the body, within the web of the wall, so that they would not delaminate and or debond, because we observed that at about 0.7% strain, FRP tends to delaminate, and we lose FRP. We had partial success in these tests. As you can see, red one is the control specimen, and there was some improvement in strength, but not a whole lot. Next, we decided to use a more ductile material. We used stainless steel sheets which had extremely high ductility. We were able to pull them up to 60% of strain and they would not rupture. So we use them, as you can see, as flexural elements connecting the wall to the foundation. Here is how they were prepared, and that would provide flexural resistance. This is masonry, while the surface bonded FRP would provide shear resistance to diagonal tension. And this is the comparison. The companion specimen had very weak resistance as being unreinforced masonry, and we only got 55 kilonewtons as opposed to about 200 kilonewtons resistance after this retrofit. And there was some ductility and energy absorption capacity, and not only that, but it had also the steel was able to, not all the steel yielded, was able to bring the specimen back to the origin as well. Now the next retrofit technique I'll be presenting is an extension of the previous one, where we cut the surface of the FRP, the concrete block units, and then drilled to the foundation and epoxy glued rebars. And we used two 15mm bars, two 15M bars, and then we covered the wall with FRP once again for shear strengthening and relied on reinforcement for flexural strengthening. But we did not fill the concrete units, and hence, even though there was a significant strength enhancement, the moment diagonal compression capacity of the masonry units were exceeded, it failed. So there was a strength enhancement. Obviously, when you retrofit URM walls, you have to perhaps use elastic concepts like expect elastic behavior. It would then be simply strength enhancement rather than ductility enhancement. So the next specimen was reserved for pre-stressing URM walls, and we did pre-stress them. As you can see, we once again used cylinders and anchored them to the foundation and applied pre-stressing. And we pre-stressed up to 500 MPa, and these strands had 1860 MPa capacity. And you can see there was a significant improvement in strength from 55 to 300, but there were many more cycles without strength decay. But this time we did fill all the gaps with concrete, and hence there wasn't any web crushing failure. Eventually it failed through toe crushing, concrete crushing. So thank you for your attention. If there are any questions I can answer, and if there's time, I'd be happy to do so.